Welcome to our channel. We are so glad you found your way here. Let us help you fall asleep. Let's begin with Enceladus, the moon that feeds the rings of Saturn. Take a slow, deep breath in and release it. Let the weight of the day fade away as we embark on an unhurried, atmospheric journey through the wonders of the cosmos. Your mind is quiet, the universe is vast, and we are ready to explore. The exploration of Enceladus began with the Voyager missions in the 1980s, which unveiled its icy surface and intriguing features. Subsequent observations by the Cassini spacecraft from 2004 to 2017 revealed the moon's dynamic nature, presenting geysers that erupt plumes of water vapor and ice particles into space. This phenomenon transformed Enceladus into a focal point for astrobiological studies, as the subsurface ocean may harbor conditions suitable for life. The significance of this moon extends beyond its potential for extraterrestrial organisms. It plays a crucial role in maintaining the stunning rings of Saturn. The particles ejected from its south polar region contribute to the ring system's composition, providing a continuous source of material that replenishes and shapes the icy bands encircling the gas giant. This interaction between Enceladus and Saturn underscores the intricate gravitational dance at play within the planet's environment. Geological activity on Enceladus also raises questions about the moon's internal structure and heat sources, suggesting a complex interplay of tidal forces and hydrothermal processes. Its surface, marked by tiger stripes, hints at the underlying ocean's movement, further enhancing its importance in understanding celestial mechanics and planetary evolution. Each discovery adds layers to the understanding of this remarkable moon and its impact on the broader cosmic landscape. Enceladus occupies a unique position within the Saturnian system, situated as the sixth largest moon orbiting the gas giant. Its proximity to Saturn places it under significant gravitational influence, which contributes to its geologically active surface. This interaction creates tidal heating, resulting in the jetting of water vapor and ice particles from its southern polar region. These plumes are not merely fascinating phenomena. They play a crucial role in feeding Saturn's A-ring, a faint but expansive ring that extends outward, shaped by this moon's continuous activity. The gravitational pull exerted by Saturn also affects the moon's orbital dynamics, influencing its eccentricity. This slight elongation in its orbit enhances the internal friction within Enceladus, further fueling its geothermal processes. The moon's surface remains largely covered in a layer of ice, which reflects sunlight, making it one of the brightest objects in the solar system. Beneath this icy shell, a subsurface ocean is believed to exist, hinting at the potential for astrobiological conditions. The interplay between Enceladus and its parent planet illustrates a complex relationship where the moon's geological activity contributes to the ring system while receiving energy from its host. This dynamic connection exemplifies the intricate web of interactions present in the Saturnian system, further enriching the scientific narrative surrounding these celestial bodies. The dimensions of Enceladus reveal a relatively small moon, measuring approximately 530 kilometers in diameter. This compact size contributes to its unique gravitational influence, resulting in a surface that exhibits a smooth, icy exterior. The shape remains predominantly spherical, a characteristic dictated by the balance of gravitational forces acting on its mass. Surface features present a stark contrast to its icy facade. The southern polar region is marked by extensive tectonic fractures known as tiger stripes, which extend across the surface. These fissures are indicative of geological activity, as they suggest the presence of subsurface oceans that may occasionally breach the icy crust. The bright, reflective quality of its surface material hints at a young age, as it appears to be continuously resurfaced and reshaped by cryovolcanic activity. Impact craters are sparse, further emphasizing the surface's youthfulness. When craters do appear, they are often shallow, suggesting that the ice may be constantly flowing, allowing for gradual alteration and erasure over time. The interaction between the Moon's interior and exterior, coupled with the ongoing geophysical processes, creates a compelling case for ongoing exploration. Observations of Enceladus continue to provoke curiosity, reinforcing its significance within the broader context of planetary science and the possibilities of extraterrestrial life. The exploration of Enceladus began in earnest with the arrival of the Voyager spacecraft in the 1980s, which provided the first detailed images of this intriguing moon. The data revealed a surface marked by a complex interplay of icy features, suggesting a dynamic environment beneath its frozen crust. Subsequent missions, particularly Cassini, significantly advanced understanding. Launched in the year 2000, it entered orbit around Saturn in 2004, acting as a sentinel to examine both the planet and its myriad moons. Cassini's observations unveiled geysers spewing water vapor and ice particles from the South Polar region, a discovery that transformed the perception of Enceladus. These plumes not only hinted at a subsurface ocean, but also contributed material to Saturn's rings, illustrating a symbiotic relationship between the Moon and the planet. The composition of the plumes, rich in organic compounds, raised questions about the potential for habitable environments beyond Earth. The ongoing analysis of data collected by these missions continues to yield insights into the Moon's geophysical processes. Each new finding adds layers to the understanding of its geological history and potential for harboring life. The quiet, icy surface of Enceladus belies the dynamism beneath, inviting further exploration in the quest to uncover its mysteries and implications for the solar system. The Cassini-Huygens mission, a collaborative endeavor between NASA, the European Space Agency, and the Italian Space Agency, played a pivotal role in revealing the complexities of Enceladus. Launched in 1997, it arrived at the Saturnian system in 2004, transforming the understanding of this moon through detailed observations. The spacecraft's close encounters provided invaluable data, particularly during its numerous flybys of Enceladus, which occurred at astonishing speeds. During these encounters, the analysis of plume activity became a focal point. Jets of water vapor and ice particles were observed erupting from the Moon's south polar region, indicating a subsurface ocean. This discovery suggested that conditions might be suitable for life, expanding the criteria for habitability beyond traditional planetary environments. The presence of organic compounds within the plumes further stimulated scientific inquiry, hinting at the potential for complex chemistry beneath the surface. Imaging data captured by Cassini revealed a landscape of fissures and ridges, suggesting active geological processes. These features, alongside temperature measurements indicating warmth beneath the icy crust, painted a picture of a dynamic world. The mission's findings emphasized the importance of Enceladus within the broader context of planetary science and astrobiology, positioning it as a significant candidate in the search for extraterrestrial life within the solar system. The icy exterior of Enceladus presents a striking contrast to the dynamic subsurface environment, composed primarily of water ice. Its surface reflects a brilliant white, indicating a largely unblemished landscape shaped by geological processes. Variations in texture reveal a complex history. Smooth plains, interspersed with rugged terrain, suggest a past marked by tectonic activity and cryovolcanism. These features are not merely aesthetic, they hint at a geological diversity that intrigues scientists. The Moon's south polar region is particularly noteworthy, revealing distinctive linear features known as tiger stripes. These fissures serve as conduits for plumes of water vapor and ice particles, erupting from the subsurface ocean below. Such activity suggests that the internal heating, likely driven by tidal forces exerted by Saturn, has created a dynamic environment critical for the Moon's geological evolution. The presence of organic molecules alongside the water ice has raised questions about the potential for life. Investigations into the surface composition have uncovered minerals, such as silicates, which indicate interactions with liquid water. This region of geological complexity invites further exploration, as each layer unravels a narrative of Enceladus' past and its potential role in hosting life. In this way, the Moon stands as a remarkable subject of study, continually revealing the intricate processes that shape celestial bodies. The E-ring of Saturn serves as a striking demonstration of the interconnectedness of celestial phenomena. Composed primarily of fine ice particles, it extends far beyond the planet's more prominent rings. The origin of this expansive structure can be traced back to the activity on Enceladus. This moon ejects plumes of water vapor and ice grains from its southern polar region, releasing material into space. These particles drift outward, gradually coalescing into the vast ring system that envelops Saturn. Observations reveal that the plumes originate from a subsurface ocean, creating a constant supply of material. This process is not merely sporadic, it operates on a continuous basis, contributing to the ring's maintenance. The interplay between Enceladus and the E-ring exemplifies the dynamic nature of satellite interactions within a planetary system. The particles released from this moon exhibit a range of sizes, with smaller grains becoming more widely dispersed. This dispersion impacts the overall density and structure of the E-ring, revealing the complexities of gravitational influences and orbital mechanics. These interactions ensure that the ring remains vibrant despite the erosive forces acting upon it. Through this delicate balance, Enceladus sustains the E-ring, highlighting its role within the broader context of Saturn's intricate and evolving environment. Tectonic activity on Enceladus reveals a surface marked by a history of dynamic processes. Fractures and ridges stretch across its icy exterior, indicating that the Moon is not merely a static body, but rather one subject to internal forces. These features suggest a subsurface ocean, with warm, liquid water beneath the frozen crust, actively contributing to the Moon's geological evolution. Observations from missions have detected plumes of water vapor and ice particles erupting from fractures known as tiger stripes. These geysers indicate that liquid water is in contact with the Moon's rocky core, fostering a unique environment potentially suitable for life. The continuous release of material into space serves as a testament to the Moon's ongoing geological activity, feeding the E-ring and demonstrating a remarkable interaction with its planetary host. The icy surface displays varying terrains, including smooth plains and rugged highlands, indicative of past tectonic events. These variations hint at a complex history of stretching and compressing forces that have shaped its current form. Evidence of tectonic movements suggests that Enceladus is undergoing a gradual evolution, governed by the interplay of gravitational forces and thermal activity. This ongoing transformation lends insight into the processes that can sustain subsurface oceans, revealing the Moon as a dynamic participant in the intricate ballet of Saturn's system. The Shringsub Dalaldova cryovolcanism defines the captivating landscape of Enceladus. This moon exhibits geysers that erupt from its southern polar region, releasing plumes of water vapor and ice particles into space. Observations reveal that these cryovolcanic features are not random occurrences, but rather a manifestation of the moon's internal heat. Tidal heating, generated by gravitational interactions with Saturn, contributes to the maintenance of a subsurface ocean, driving the geysers to spectacular heights. The plumes, often spanning several hundred kilometers into the void, are a source of material that feeds Saturn's E-ring. The composition of these ejections includes not only water, but also organic molecules, salts, and other compounds. Such findings suggest the potential for chemical processes akin to those that support life on Earth. The frequent and sustained activity of these geysers emphasizes the dynamic nature of this moon. Instruments aboard spacecraft, like the Cassini orbiter, have captured detailed images and data from these eruptions. Analysis of the water vapor reveals the presence of complex organic compounds, provoking discussions regarding the moon's habitability. This continuous cycle of ejection and replenishment shapes the surrounding environment, showcasing the interplay between the moon and the broader Saturnian system. Observations continue to deepen understanding of cryovolcanism's role in shaping celestial bodies. Temperature analysis reveals intriguing insights into surface and subsurface thermal dynamics. Measurements indicate that the surface of Enceladus maintains an average temperature of approximately 173 Kelvin, an icy expanse with varying thermal characteristics. These cold conditions create a stark contrast with the warmer regions believed to exist beneath the crust, where heat generated through tidal forces results in localized thermal anomalies. Subsurface heat plays a crucial role in driving the observed geysers. The interaction between gravitational pull and the moon's eccentric orbit generates friction, producing sufficient thermal energy to sustain a subsurface ocean. This ocean, beneath the icy shell, may reach temperatures capable of supporting liquid water. The geysers erupt from fractures, releasing plumes rich in water vapor and organic compounds, contributing to Saturn's extensive ring system. Thermal modeling suggests that the icy crust insulates the ocean beneath, creating a delicate balance between heat retention and escape. These dynamics are essential for understanding the moon's geological activity and potential habitability. Analysis of temperature variations across the surface allows scientists to identify regions of interest for further exploration. Understanding these thermal processes offers a glimpse into the complex interplay between geological forces and cryovolcanism, revealing the intricacies hidden within this fascinating moon. Insights gained extend beyond Enceladus, informing broader planetary science regarding icy bodies in our solar system. The plumes of Enceladus offer a fascinating glimpse into the moon's subsurface ocean, revealing a wealth of information regarding its composition. Erupting from deep fractures known as tiger stripes, these icy jets propel fine particles and vapor into space, contributing to Saturn's E-ring. The material consists primarily of water vapor, with traces of organic compounds and salts. Such a combination suggests a complex chemistry occurring beneath the Moon's icy crust. Ejector mechanics play a crucial role in understanding these plumes. The process begins with pressure buildup in the subsurface ocean caused by tidal heating from Saturn's gravitational pull. This heating keeps the water in a liquid state despite the frigid surface temperatures. As pressure reaches a critical threshold, the water escapes through the cracks, carrying with it a mixture of ice particles and gases. Once released, the plume expands and disperses, forming intricate patterns as it interacts with Saturn's magnetosphere. The dynamics of these jets are influenced by Enceladus's relatively low gravity, which allows the ejector to rise high into space before falling back to the surface or being entrained by Saturn's magnetic field. This mechanism not only supplies material to the rings, but also continues to intrigue scientists studying the potential for life in such extreme environments. The ongoing exploration of these features reveals the Moon's active geologic past and its role within the larger context of the Saturnian system. The subsurface ocean of Enceladus is a critical component in understanding its geological activity and potential for supporting life. Hidden beneath a thick layer of icy crust, this ocean is believed to be in contact with the Moon's rocky mantle, allowing for complex chemical interactions. Observations from the Cassini spacecraft have revealed plumes of water vapor and organic compounds erupting from the southern polar region, providing compelling evidence of this hidden ocean's existence. These geysers indicate a dynamic system where hydrothermal activity may occur, suggesting that the ocean is not simply stagnant, but rather an active environment. The presence of salts and other materials in the ejected plumes implies a rich chemistry that could support microbial life. Analyzing these ejecta has provided insights into the ocean's composition, enriching our understanding of the Moon's potential habitability. Further implications arise when considering the Moon's interactions with Saturn's rings. The fine particles expelled from the geysers contribute to the formation and maintenance of the E-ring, demonstrating a direct relationship between this moon and the larger planetary system. The continual replenishment of the ring material highlights the interconnectedness of celestial bodies within the Saturnian environment, pointing to a complex ecosystem where Enceladus plays a vital role. The ongoing studies of this moon continue to reshape the understanding of ocean worlds beyond Earth. The presence of salt in the ocean beneath the icy crust of Enceladus indicates potential for unique chemical reactions that could support life. Measurements suggest a saline composition similar to Earth's oceans, which raises intriguing questions about habitability within this distant environment. Salinity levels play a crucial role in determining the types of organisms that might thrive, as they influence both the physical and chemical properties of the water. Interactions between the ocean's water and the rocky seafloor generate essential nutrients, potentially creating a suitable habitat for microbial life. The release of hydrogen and other compounds during these interactions forms a chemical energy source, which can sustain biological processes. These factors contribute to the growing hypothesis that life may exist in the subsurface ocean of Enceladus. The plumes erupting from its southern polar region further support this idea. These geysers, rich in water vapor, organic molecules, and salts, provide direct evidence of the ocean's composition and its potential for supporting diverse ecosystems. The study of such ejecta allows researchers to gather samples without the need for direct exploration, facilitating an understanding of the moon's biological potential. The implications of these findings extend beyond just Enceladus, inviting comparisons with other icy bodies in the solar system, including Europa and Ganymede. Understanding the saltiness of this ocean not only informs the search for extraterrestrial life, but also enhances the study of ocean worlds overall. The presence of organic compounds within the icy crust of Enceladus raises intriguing possibilities regarding the Moon's capacity to support life. Analysis of plumes ejected from its south polar region reveals a complex mixture of water vapor, salts, and organic molecules. These findings suggest that the subsurface ocean contains the essential building blocks for life. Such compounds include simple hydrocarbons, which are fundamental to biological processes, indicating a potential for chemical reactions akin to those that sustain life on Earth. This region exhibits conditions that could promote chemical pathways leading to prebiotic life. The interaction between the ocean and the Moon's rocky core is of particular interest. Hydrothermal vents, similar to those found on Earth, may provide a nutrient-rich environment where organic compounds could undergo transformations conducive to life. The geochemical processes occurring here also contribute to the dynamic nature of the ocean, influencing its composition and potential habitability. These organic molecules of Ansev dormite of our deuterating organic molecules, combined with the abundant energy sources from hydrothermal activity, create a compelling case for Enceladus as a candidate in the search for extraterrestrial life. Understanding the geochemistry of this ocean world expands our knowledge of where life might emerge beyond our planet, challenging preconceived notions about habitability in the solar system and beyond. The interactions between this moon and Saturn's magnetosphere are intricate and profound. Enceladus possesses a weak intrinsic magnetic field, but its surface is shaped by the powerful magnetic forces exerted by the gas giant. This gravitational relationship results in a unique environment where charged particles are constantly colliding with the Moon's icy crust, leading to significant geological and atmospheric phenomena. Electrons and ions from Saturn's magnetosphere interact with the plume emissions, creating a dynamic exchange of energy. This process contributes to the formation of a complex electric field around Enceladus, which in turn influences its geysers. The particles ejected from the subsurface ocean are not merely water vapor. They carry a mix of organic compounds and salts, expelled into the vastness of space. The magnetic field plays a critical role in shaping the trajectory and dispersion of these plumes, guiding them into Saturn's ring system. As these particles, enriched with essential elements, enter the rings, they provide additional material for their ongoing evolution. This interaction exemplifies the interconnectedness of celestial bodies within the Saturnian system, highlighting how Enceladus contributes to the broader dynamics at play. These processes underscore not only the Moon's geological activity, but also its significance in understanding the magnetospheric environment surrounding Saturn. Tidal heating plays a crucial role in shaping the geological landscape of Enceladus. The Moon's orbit around Saturn is not perfectly circular, resulting in varying gravitational forces. This eccentricity generates internal friction, which in turn heats the Moon's icy crust. The warmth produced by these forces leads to the melting of subsurface water, creating vast reservoirs beneath the surface. These reservoirs contribute to the active plumes that erupt from the south polar region, releasing water vapor and organic compounds into space. Such eruptions indicate a dynamic subsurface ocean where conditions may be suitable for life. The interaction between the icy crust and the underlying liquid water fosters a unique environment, rich in chemical diversity. Surface features, including fissures and ridges, provide further evidence of this ongoing geological activity. The icy crust is continually reshaped as it responds to the stresses induced by tidal forces. The landscape exhibits signs of recent geological processes, highlighting its youth relative to other celestial bodies within the solar system. Observations reveal that the expelled material not only contributes to Saturn's rings but also interacts with the magnetosphere, affecting particle dynamics and energy distribution. The interplay between tidal heating and geological activity makes Enceladus an intriguing subject within planetary science, illustrating the complex relationships between celestial bodies and their environments. Comparative analysis illustrates distinct characteristics among ocean worlds such as Enceladus and Europa. Both moons exhibit subsurface oceans, yet their geological processes diverge significantly. While Enceladus showcases active geysers that eject plumes of water vapor and ice particles into space, Europa maintains a more subdued expression of activity beneath its icy crust. Surface features on Europa include ridges and a disrupted terrain, hinting at a dynamic interior. Though direct evidence of cryovolcanism remains elusive, variations in composition further differentiate these celestial bodies. Enceladus's plumes contain organic compounds, suggesting a rich chemical milieu that may support microbial life. In contrast, Europa's surface is predominantly water ice, with potential for a more pristine environment, though the subsurface ocean remains a point of speculation regarding its habitability. Other ocean worlds, such as Ganymede and Titan, also contribute to this comparative landscape. Ganymede, the largest moon in the solar system, possesses a magnetic field and potentially a salty ocean beneath its icy shell. Titan, with its dense atmosphere and methane lakes, offers a starkly different but equally intriguing perspective on extraterrestrial environments. These comparisons highlight the diverse evolutionary paths of ocean worlds, revealing the myriad ways in which celestial bodies can interact with their surroundings and each other. The potential for life beyond Earth finds a compelling candidate in Enceladus, a moon whose icy exterior conceals a subsurface ocean. This region maintains a unique environment where hydrothermal activity may offer the necessary conditions for life. Jets of water vapor and organic compounds erupt from its south pole, suggesting a dynamic interplay between the ocean beneath and the surface. These plumes provide invaluable clues about the moon's composition and the processes occurring within its ocean. The presence of simple organic molecules fuels speculation regarding the building blocks of life. Observations from the Cassini spacecraft revealed that these geysers contain not only water but also salts, silica, and other chemicals that are critical for biological processes. The hydrothermal vents on the ocean floor could create a habitat similar to those found on Earth, where extremophils thrive in the absence of sunlight. Such environments support the idea that if life exists on Enceladus, it could take forms adapted to extreme conditions. Scientific interest in this moon continues to grow, with future missions aimed at further exploring these intriguing features. Understanding the potential for life in such places could reshape our perception of habitability and the distribution of life in the cosmos. This exploration represents a pivotal step toward answering profound questions about life beyond our planet. Spectroscopy studies reveal the complex composition of Enceladus's surface and its intriguing plumes. By analyzing light reflected off its icy exterior, the presence of organic compounds becomes evident. These substances suggest a rich chemical environment, raising tantalizing possibilities regarding the moon's potential for supporting life. The plumes, observed erupting from the southern polar region, of Night Alsace and Night Southern Polar region provide a constant source of material that feeds into Saturn's rings, composed primarily of water vapor. These geysers also contain salts and organic molecules, hinting at the Moon's subsurface ocean. This active geology is a focal point for researchers who utilize spectroscopic techniques to decode the spectral signatures emitted from these emissions. Data collected during close flybys allows scientists to map the distribution of various compounds across the surface. The varying reflectivity of different regions indicates a diversity of materials, possibly shaped by cryovolcanism or other geological processes. Observations show that some areas may contain carbonates, which are often associated with biological activity in terrestrial environments. Understanding the interaction between the plumes and the surrounding environment offers insights into the Moon's history and evolution. These findings contribute to a broader comprehension of ocean worlds in our solar system, establishing Enceladus as a key subject in the ongoing quest to uncover the mysteries of celestial bodies and their capacity for life. The role of ice shell thickness emerges as a crucial factor in understanding the dynamics of Enceladus ocean. Variations in this thickness influence the exchange of heat between the subsurface ocean and the icy crust above. Thermal gradients manifest, shaping not only the ocean's potential habitability, but also the geological activity observed on the surface. Data indicate that certain regions exhibit a thinner ice shell, facilitating tidal heating, which in turn supports the existence of liquid water beneath. Such geological features, including the prominent tiger stripes, provide insights into the processes at play beneath the surface. These fractures suggest that the icy crust is responding to the gravitational interactions with Saturn, resulting in flexing and deformation. This interaction generates sufficient heat, allowing for the maintenance of a subsurface ocean that is likely rich in nutrients. Understanding the thickness of the ice shell also informs models of ocean circulation. Variability in thickness could lead to differing ecological zones, with potential implications for the development of life. The interplay between the ice and ocean acts as a protective barrier, while simultaneously allowing for nutrient exchange, creating an environment that may be conducive to biological processes. Ongoing observations will continue to refine the understanding of these dynamics, revealing more about this enigmatic moon's capacity for life. The south pole of Enceladus represents a distinct area of scientific curiosity, uniquely characterized by its geysers. This region emits plumes of water vapor and ice particles, creating a potential barrier to the moon's surface. Spectroscopic analysis indicates the presence of organic molecules, hinting at the chemical complexity that might support microbial life. Observations reveal that these geysers likely originate from a subsurface ocean insulated beneath a thick crust of ice. Temperature measurements indicate variations in heat flow, suggesting geological activity beneath the surface. This warmth is essential, as it may facilitate the interaction of water with minerals, fostering a chemistry that could be conducive to life. The interaction between the subsurface ocean and the icy crust is of particular interest, as it may allow for nutrient exchanges that nourish any potential ecosystems. Geophysical studies have demonstrated that the South Pole is not static. Tectonic features, including ridges and fractures, indicate a dynamic landscape shaped by internal processes. The influence of tidal flexing, driven by Saturn's gravitational pull, contributes to this ongoing activity. These geological phenomena provide insight into the Moon's history and evolution, offering a window into the conditions that prevail in this icy world, where the potential for life remains tantalizingly within reach. Impact cratering has played a significant role in shaping Enceladus's surface and geological history. The scars left by these collisions tell a story of a dynamic and ever-changing environment. Each impact has the potential to disrupt the icy crust, creating fissures that may extend deep into the Moon's subsurface ocean. These events provide pathways for the release of water vapor and other materials, contributing to the plume activity observed at the South Pole. The frequency and distribution of impact craters across the Moon's surface indicate a complex interplay between internal geological processes and external forces. Younger regions, characterized by fewer craters, suggest a relatively recent resurfacing, perhaps due to cryovolcanism or tectonic activity. In contrast, heavily cratered areas reveal a more ancient history, marked by the relentless bombardment of celestial debris. Analyzing the size and distribution of craters allows scientists to estimate the Moon's surface age and the frequency of significant impact events. This understanding enhances the broader context of Enceladus within the Saturnian system. The interaction between impacts and internal ocean dynamics may also influence the potential for habitability, as energy from these collisions could create localized heating that sustains microbial life in the subsurface ocean. The intricate balance of these factors underscores the significance of impact cratering in the evolutionary narrative of this intriguing moon. 109's geothermal activity plays a crucial role in shaping the surface and subsurface characteristics of this moon. Observations reveal that the interior remains geologically active, a phenomenon driven by tidal heating. This heating arises from gravitational interactions with Saturn and its other moons, resulting in a dynamic environment beneath the icy crust. The presence of liquid water beneath the surface is one of the most compelling outcomes of this activity. These subsurface oceans harbor the potential for chemical reactions that could support microbial life. Hydrothermal vents, akin to those found on Earth, may exist within this watery realm, providing an energy source for life forms. Such environments foster unique ecosystems, suggesting that life's building blocks could develop in unexpected locations. Continued eruptions from the southern polar region, which eject plumes of water vapor and ice particles into space, serve as a direct indicator of this geothermal activity. These geysers contribute to the formation of Saturn's rings, feeding the icy particles that give the rings their distinct structure. The analysis of these plumes offers insights into the Moon's composition and the conditions that prevail beneath the surface. Understanding this geothermal process enhances knowledge of planetary habitability in the broader context of our solar system. The study of Enceladus continues to provoke intriguing questions about life beyond Earth. Seasonal changes on Enceladus have revealed distinct variations in surface and plume activity, providing critical insights into its dynamic environment. The Moon experiences a tilt of roughly 1 degree, resulting in a subtle shift in sunlight exposure across its surface. This slight axial tilt causes thermal variations that impact the behavior of its icy crust during the warmer months. Increased solar energy contributes to the melting of surface ice. This melting can lead to the formation of transient features, including areas of fresh ice and shifting surface textures. The presence of these features suggests a degree of geological activity, hinting at an active subsurface ocean. Plume activity fluctuates in tandem with these seasonal changes. Observations indicate that geysers, which eject water vapor and organic molecules, tend to intensify during certain periods, likely linked to the warming of the surface and the resulting pressure changes in the subsurface ocean. These plumes, extending hundreds of kilometers into space, serve as a crucial link between the Moon's interior and the outer environment, contributing material to Saturn's rings. As the seasons progress, varying plume intensity and surface alterations provide valuable data.
This ongoing transformation fosters a deeper understanding of Enceladus, underscoring its role in the broader context of planetary science and the search for extraterrestrial life. Enceladus possesses a unique gravity field which offers insights into its internal structure and composition. Measurements from gravitational interactions reveal variations that suggest a differentiated interior. It is believed that beneath the icy crust lies a subsurface ocean, a significant factor in understanding the Moon's geophysical processes. This ocean may extend to depths of several kilometers, nestled between layers of ice and rock. The gravitational pull experienced on its surface varies, indicating denser regions beneath the crust. These variations are instrumental in mapping the distribution of mass and identifying potential reservoirs of liquid water. Such findings raise intriguing questions about the Moon's thermal state and the mechanisms that sustain this subsurface ocean. Observations from missions have confirmed the presence of geysers erupting from its south pole, which further reinforces the idea of an active geological environment. The expelled plumes consist of water vapor and organic molecules, hinting at the possibility of life-sustaining conditions beneath its icy facade. Understanding the gravity field of Enceladus not only sheds light on its internal structure, but also suggests dynamic interactions between its ocean and the surface. This interplay is crucial in shaping the Moon's geology and contributes to the intricate processes that feed Saturn's majestic rings. Such dynamics paint a picture of a world constantly in flux, ripe for exploration and discovery. The gravitational interplay between Enceladus and Saturn's rings creates a fascinating relationship. This moon, measuring approximately 510 kilometers in diameter, exerts a subtle influence on the icy particles that compose the rings as it orbits. The tidal forces generated by Saturn's immense gravity lead to significant geological activity on its surface. This activity manifests in the form of geysers that eject plumes of water vapor and ice into space. These plumes contribute directly to the ring system, enriching it with fresh material. The ejected particles, propelled by their own momentum, drift towards the rings, where they join the existing substances, replenishing their icy composition. This constant infusion of new material helps maintain the ring's brightness and structural integrity, ensuring they remain vibrant and dynamic. Interactions between Enceladus and the rings also produce intricate patterns within the ring structure. Small gravitational perturbations caused by the Moon's orbit can create gaps and waves in the ring particles, reflecting the delicate balance of forces at play. Scientists have identified a particularly pronounced gap known as the Enceladus gap, which serves as a testament to this moon's role in shaping its environment. Understanding this relationship provides critical insights into the evolving dynamics of Saturn's rings and their connection to the celestial bodies that inhabit this region. The formation of Saturn's E-ring can be traced back to the icy plumes emanating from Enceladus's surface. These jets, rich in water vapor and organic compounds, contribute significantly to the ring's material. This moon serves as a primary source, continuously replenishing particles that drift through the faint structure of the E-ring. The composition of these emissions reveals a complex interaction between the moon's internal ocean and the outer icy crust, suggesting a dynamic environment beneath. Particles ejected from Enceladus are subject to various forces, including Saturn's gravitational pull and electromagnetic interactions. As they escape the moon's gravity, they disperse into the surrounding space, forming a halo of fine ice grains. Over time, these grains coalesce to create the delicate structure of the E-ring, a phenomenon that underscores the moon's influence on its celestial surroundings. The ongoing activity of Enceladus directly affects the ring's density and distribution. Variations in the plume's output lead to fluctuations in the E-ring's characteristics, illustrating a feedback loop between the moon and the ring system. This relationship highlights the interconnected nature of celestial bodies, where one significantly influences the other's evolution. The study of these interactions deepens our understanding of planetary ring systems and their origins, further unraveling the complexities of our solar system. The dynamic environment of Enceladus reveals a landscape constantly shaped by both internal and external forces. This moon's surface, primarily composed of water ice, exhibits a variety of geological features, including ridges, fractures, and expansive plains. The temperature variations across the surface contribute to a unique weather system driven by its subsurface ocean. Thermal activity beneath the icy crust generates plumes that eject water vapor and ice particles into space, creating a transient yet impactful atmosphere. These plumes, observed by the Cassini spacecraft, demonstrate how the internal heat influences surface morphology. The interplay between cryovolcanism and the freezing temperatures of the outer crust results in a landscape that is neither static nor predictable. Changes can occur over relatively short time spans, creating new surface features while erasing older ones. The presence of organic compounds within the ejected materials hints at chemical processes that may support life. This potential biochemistry is closely tied to the moon's geophysical dynamics. The subsurface ocean, kept warm by tidal heating from gravitational interactions with Saturn and its other moons, presents a stable environment for chemical reactions. Investigating Enceladus offers crucial insights into the conditions that might allow life to exist elsewhere in the universe, while also enhancing knowledge of icy moon geology and the processes that maintain their surfaces. The potential for future missions to Enceladus presents an opportunity to deepen understanding of this intriguing moon. Researchers have proposed several objectives, including the analysis of its subsurface ocean and the eventual exploration of its plumes, which are known to eject water vapor and organic compounds into space. These plumes may harbor the building blocks of life, making them prime targets for astrobiological investigations. Challenges arise in the form of technological and logistical hurdles. Reaching Enceladus requires advanced propulsion systems capable of traversing vast distances efficiently. Furthermore, the environment, with its extreme cold and radiation from Saturn, necessitates robust spacecraft design. Instruments must be resilient enough to collect data and samples without contamination. The scientific community also emphasizes the importance of collaboration. Multinational partnerships could pool resources, knowledge, and expertise, increasing mission viability. In addition, developing sophisticated robotics will be essential for surface exploration. The prospect of landing on the icy crust poses another significant challenge. Understanding the geological processes shaping its surface could provide insight into the moon's history and its potential habitability. Each mission carries the weight of uncovering profound truths about not only Enceladus, but also the broader cosmos. As technology progresses, these endeavors illuminate pathways toward discovery. Enceladus plays a vital role in the intricate dynamics of planetary systems, particularly in its interactions with Saturn and its stunning ring system. This moon is not merely a celestial body. It serves as a significant contributor to the ongoing processes that shape the environment within its orbit. The geysers that erupt from its south pole release plumes of water vapor and ice particles into space, injecting material into Saturn's rings. The particles that escape contribute to the ring's density and composition, underscoring the interconnectedness of moons and their planets. These features make Enceladus a focal point in comparative planetology. By studying its geology and cryovolcanism, scientists gain insights into other icy worlds within the solar system. The icy crust, punctuated by fractures and surface features, hints at a dynamic interior possibly sustained by tidal heating. This process may also occur on other celestial bodies, such as Europa and Ganymede, inviting comparisons that enhance understanding of potential habitability beyond Earth. The plumes, rich in organic compounds, raise questions about the potential for life in environments previously considered inhospitable. These findings encourage exploration beyond the familiar, inspiring missions that seek to unravel the mysteries of similar icy worlds scattered throughout the cosmos, each one a potential harbor for life. The gravitational influence of Saturn profoundly shapes Enceladus, dictating its orbital dynamics and geological behavior. This moon, locked in a delicate gravitational embrace, experiences significant tidal forces as it traverses its elliptical orbit. These forces induce internal heating, a phenomenon that contributes to the moon's active subsurface ocean and, consequently, its striking geysers. Enceladus orbits Saturn in a synchronized rhythm, influenced by the gravitational pulls of neighboring moons. This gravitational interaction creates a balance, maintaining its orbit while simultaneously fueling the geological activity observed on its surface. The consistency of this activity suggests a complex interplay between internal pressures and external forces, resulting in the continuous eruption of water vapor and organic compounds from its icy crust. The gravitational field is not merely a backdrop. It acts as a catalyst for Enceladus's evolution. The variations in gravitational pull as it orbits Saturn create stress on the moon's icy shell, leading to fractures and fissures. These openings allow the subsurface ocean to escape, forming plumes that contribute to Saturn's rings. The resulting particles, composed of water ice and other materials, enrich the ring system, illustrating a profound connection between the two celestial bodies. This dynamic relationship highlights the role of gravity in shaping the characteristics of moons and their potential contributions to the surrounding celestial environment. Theories regarding the formation of this intriguing moon suggest that it originated from the primordial material surrounding Saturn, coalescing through processes typical of celestial mechanics. Formation models indicate that Enceladus likely experienced significant heating due to tidal forces exerted by its massive parent planet. These forces generated enough energy to facilitate the internal differentiation of materials, leading to a layered structure. Current understanding posits that a subsurface ocean exists, maintained in a liquid state by heat from radioactive decay and tidal heating. This ocean is crucial as it serves as a reservoir for the plumes seen erupting from its south polar region. These geysers, Releasing particles into space suggest a dynamic geological history and an active interior. Observations from missions such as the Cassini spacecraft have provided vital data supporting the hypothesis of this hidden ocean and its complex interactions with the icy crust above. The presence of organic compounds and other chemicals in the plumes suggests that the ocean may harbor conditions suitable for life. In addition to its potential habitability, the moon's surface is marked by fractures and ridges, indicating geological activity.
This ongoing dynamism reflects a young surface, suggesting that Enceladus continues to evolve within the gravitational embrace of Saturn, contributing to its own narrative within the broader context of the solar system. The potential for habitability on Enceladus is a subject of significant interest among planetary scientists. Beneath its icy crust lies a subsurface ocean, a vast reservoir of liquid water that could harbor the conditions necessary for life. This ocean is in contact with the moon's rocky mantle, allowing for chemical interactions that may lead to the production of organic compounds, essential building blocks for life. The plumes of water vapor and ice crystals ejected from its south polar region provide direct evidence of this subsurface ocean. The analysis of these plumes reveals not only water, but also organic molecules and salts, hinting at a rich and complex environment. Such findings raise questions about the processes occurring beneath the surface and their implications for potential microbial life. And Saturn's gravitational influence plays a crucial role in maintaining this liquid ocean, creating a dynamic environment that may facilitate a variety of chemical reactions. These conditions are reminiscent of those found in some of Earth's most extreme habitats, such as deep-sea hydrothermal vents, where life thrives despite harsh conditions. Studying Enceladus contributes to a broader understanding of where life might exist beyond Earth. The moon serves as a compelling laboratory for examining the intricate dance between geology and potential biological processes in the cosmos. These explorations deepen our knowledge of the conditions necessary for life and expand the horizons of astrobiology. The intricate dynamics between Saturn's rings and Enceladus significantly influence surface processes. Gravitational interactions induce tidal heating within the moon, generating energy that drives geological activity. This energy manifests as geysers erupting from the ice crust, releasing plumes of water vapor and organic molecules into space. The proximity to the rings contributes to the constant bombardment of micrometeorites, which erode the surface and create a unique topography. On the icy surface exhibits a variety of terrain types, including smooth plains and fractured regions shaped by these continuous processes. The plumes themselves, rich in salts and other compounds, hint at subsurface oceans, suggesting a complex interplay between the moon's internal ocean and external influences. The ejected materials from the geysers contribute to the ring system, recycling elements and creating a tenuous link between the moon and its planetary companion. This region also experiences variations in temperature, driven by the heat from the moon's core and the absorption of sunlight by the ring particles. Such temperature fluctuations result in cryovolcanism, where substances like water, ammonia, and methane can erupt, further shaping the landscape. These interactions illustrate a dynamic environment, one where Enceladus continuously evolves, shaped by the gravitational embrace of Saturn and its magnificent rings. Cryovolcanic activity defines much of Enceladus's character, driving the release of water vapor and icy particles into space. This phenomenon occurs through a series of fractures known as tiger stripes, located near the moon's south pole. These linear features serve as conduits for subsurface water, which under immense pressure finds its way to the surface. The process is governed by the intricate interplay of temperature, pressure, and the unique composition of the Moon's icy crust. The frequency of eruptions varies, with some events occurring in regular intervals, while others appear sporadic. Observations from missions such as Cassini have revealed plumes that can shoot hundreds of kilometers into space, contributing to the E-ring of Saturn. The mechanisms behind these eruptions are still subjects of scientific inquiry. It is believed that tidal heating caused by gravitational interactions with Saturn and neighboring moons plays a pivotal role, generating sufficient heat to maintain a subsurface ocean beneath the thick ice shell. Chemical analysis of the ejected material reveals a rich composition of organic compounds, suggesting that this moon holds ingredients essential for life. Each plume offers a glimpse into the moon's hidden ocean, providing vital clues about its geothermal processes and the potential for habitability in the icy depths. Geological mapping techniques reveal the intricate details of Enceladus' surface, showcasing a landscape shaped by both internal and external forces. The icy crust displays a network of fractures and ridges, indicative of tectonic activity. Thermal imaging, coupled with radar measurements, helps scientists understand the varying temperatures across these features. Warmer areas often correlate with active geysers, suggesting ongoing geological processes beneath the surface. Spectroscopic analysis identifies the composition of surface materials, revealing a landscape rich in water ice and various salts. These chemical signatures provide insights into the Moon's oceanic environment and the interactions between the ocean and the icy shell. The presence of organic molecules within the plume material further enhances the potential for biological activity in the subsurface ocean. High-resolution imaging obtained from passing spacecraft captures the stark contrasts between smooth plains and rugged terrains, painting a picture of a dynamic geological history. Crater counts enable researchers to estimate the age of different regions, indicating areas where the surface is young and geologically active versus more ancient, stable regions. Every detail of this icy world contributes to a broader understanding of planetary processes. Investigating these features helps inform theories about similar celestial bodies and their capacity to harbor life, reinforcing the importance of Enceladus in the study of astrobiology. The subsurface ocean beneath the icy crust plays a significant role in shaping the Moon's geophysical characteristics. Silicate materials, found in the ocean's depths, interact with the water and contribute to a unique chemical environment. This interaction not only provides essential nutrients, but also raises questions about the potential for life. The presence of silicates contributes to the formation of hydrothermal vents, which have been observed on other celestial bodies as potential sites for microbial ecosystems. The complex chemistry resulting from these silicate interactions enhances the ocean's capacity to support biological processes. This region may host a rich array of organic compounds essential for the development of life. The heat generated by tidal forces further influences this environment, creating a dynamic system where water and minerals flow freely, fostering a habitat that could sustain life forms. In addition, the silicate-rich ocean contributes to the production of icy plumes that erupt from the surface. These plumes, which contain water vapor, organic molecules, and silicate particles, play a crucial role in feeding the rings of Saturn. The ejected materials enrich the ring system, creating a continuous cycle of interaction between the Moon and its planetary companion. Understanding these processes provides insight into the fundamental mechanisms that could support life in extreme environments, illuminating the broader implications for planetary science. Frost formation on Enceladus reveals a complex geological history marked by tectonic activity and cryovolcanism. This moon's icy exterior is not merely a static surface. Rather, it reflects a dynamic interplay between internal heat and the frigid vacuum of space. Evidence suggests that beneath the crust lies a subsurface ocean kept liquid by the heat generated from tidal forces exerted by Saturn's gravitational pull. The geological features observed include ridges, fractures, and chaotic terrains, indicative of past tectonic movements. These formations indicate that the crust has undergone significant changes over time, shaped by processes akin to those found on Earth. In some regions, the ice appears to have been recycled, hinting at an active resurfacing mechanism propelled by the underlying ocean. The evolution of this crust is crucial in understanding the moon's thermal history and the potential for habitability. The presence of hydrothermal activity, possibly at the ocean floor, suggests that chemical reactions can occur, creating conditions favorable for life. This unique environment may mirror early Earth conditions, providing clues about how life could emerge in similar settings across the cosmos. These insights into the geological past of Enceladus enhance the understanding of icy moons and their role in the broader context of planetary evolution and habitability in our solar system. The presence of Saturn, a gas giant with a formidable gravitational field, profoundly influences the characteristics of Enceladus. This proximity subjects the moon to significant tidal forces, resulting in the heating of its interior. As these forces interact with the moon's icy crust, they facilitate the ongoing geological activity observed on its surface. Geysers erupt from its south polar region, ejecting water vapor and organic compounds into space, contributing to the intricate structure of Saturn's rings. The composition of these plumes indicates a complex subsurface ocean enriched with minerals and potential nutrients. This environment is crucial for studying the processes that govern habitability beyond Earth. The exchange of materials between Enceladus and Saturn's rings influences both celestial bodies as the moon continuously replenishes the icy particles that enhance the ring's brightness and density. Furthermore, the interaction between the moon and Saturn's magnetosphere creates a dynamic atmosphere around Enceladus. Charged particles from the magnetosphere bombard its surface, resulting in chemical reactions that may further support prebiotic chemistry. The delicate balance of these processes reflects the intricate relationship between the moon and its parent planet, shaping not only its physical attributes, but also its potential role in the ongoing search for life beyond our planet. Chemical exchanges occur at the interface of Enceladus and Saturn's atmosphere. The moon's icy surface sustains active geysers, which expel a plume of water vapor and other organic compounds into space. This ejected material interacts with the surrounding environment, creating a dynamic exchange. The sputtering of ions from Saturn's magnetosphere contributes to this process, stripping away molecules from the moon's surface and altering its chemical composition. The composition of these plumes offers crucial insights. Detected elements such as sodium, carbon dioxide, and methane hint at complex organic chemistry, suggesting that these compounds may play a role in the moon's subsurface ocean. The interaction with Saturn's atmosphere further enriches the chemical landscape as particles from the rings amalgamate with the plume, introducing additional molecules into the environment. Fusion's strong gravitational pull influences the trajectory of these emissions, allowing them to become part of the rings feeding them with organic material. This interaction illustrates how the Moon not only contributes to its planetary system's physical structure, but also engages in a broader environmental dialogue with its surroundings. Understanding these exchanges is vital for assessing the potential habitability of Enceladus, as they may indicate the presence of essential ingredients for life hidden beneath its icy crust. The Moon's geophysical processes provide vital clues regarding the early solar system.
This region, characterized by its icy surface and subsurface ocean, serves as a time capsule, preserving conditions similar to those present during the formation of the solar system. Analyzing the spewing plumes reveals the composition of these ancient waters, offering insights into the primordial materials that shaped planetary bodies. Immersive embodies the solar system. These findings suggest that similar conditions could be found elsewhere, extending the scope of potential habitability beyond familiar terrestrial realms. The gravitational interactions with Saturn also contribute to the dynamic environment, influencing tidal heating, which plays a crucial role in sustaining the subsurface ocean. The Moon's unique characteristics allow scientists to study geological processes in real time, illustrating how internal heat and tectonic activity can shape a moon's evolution. This continuous interaction between the surface and subsurface environments enhances our understanding of celestial mechanics and the diverse outcomes of planetary formation. Through Enceladus, researchers gain a clearer perspective on the complexities of early solar system evolution, revealing the interconnectedness of celestial bodies and the potential pathways for life in the cosmos. These revelations underscore the significance of this icy moon in the broader narrative of planetary science. The surface temperature of this moon plays a critical role in astrobiological studies, averaging around -300 degrees Fahrenheit. The extreme cold influences the physical and chemical processes occurring on its surface and within its subsurface ocean. These frigid conditions maintain a delicate balance, preserving organic compounds and other potentially life-supporting materials that may exist within the icy shell. This environment creates a unique opportunity to study the potential for life beyond Earth. The geothermal activity, evidenced by the plumes of water vapor and ice that erupt from the surface, indicates that beneath the frozen exterior lies a dynamic ocean. The interaction between this ocean and the rocky core could provide the necessary conditions for life, similar to those found in Earth's deep-sea hydrothermal vents. Temperature measurements taken during flybys and analyses of surface features contribute to understanding how heat is generated and distributed. The distribution of thermal anomalies hints at geological processes that could support microbial ecosystems in the hidden depths. Studying the surface temperature also assists in modeling the moon's climate and the stability of its subsurface ocean over geological timescales. Insights gained from these investigations enhance knowledge of the potential habitability of icy worlds in the outer solar system, drawing attention to the broader implications for life in varied environments. Geologic activity on Enceladus reveals a complex history, marked by processes that have shaped its icy surface over eons. The presence of a subsurface ocean suggests that liquid water exists beneath the thick ice crust, likely influencing tectonic activity. Features such as ridges and fractures indicate ongoing geological processes. These characteristics imply that the moon has experienced significant tectonic reshaping, with ice tectonics possibly driven by tidal heating resulting from gravitational interactions with Saturn. The timeline of activity is underscored by the moon's unique geysers, which intermittently expel plumes of water vapor and ice particles into space. Observations from the Cassini spacecraft have confirmed that these geysers are concentrated at the South Pole, where a region known as the Tiger Stripes showcases a network of deep fissures. The plumes contain organic compounds and other chemicals that hint at potential biological processes occurring in the ocean beneath the surface. Dating the surface features reveals a relatively young landscape, suggesting that the icy crust is continually renewed. Evidence of cryovolcanism, volcanic activity involving the eruption of icy materials, further supports the notion that Enceladus remains geologically active. This ongoing activity not only enriches the rings of Saturn but also raises questions about the Moon's capacity to harbor life within its hidden ocean. Ice muffled leaf within this icy moon positions it as a prime target in the search for extraterrestrial organisms within the solar system. Enceladus possesses a subsurface ocean, warmed by tidal forces that could create conditions favorable for microbial life. These factors have intensified interest among scientists, leading to extensive studies and missions aimed at unraveling its mysteries. Plumes of water vapor and organic materials have been ejected into space, providing tantalizing evidence of the Moon's dynamic environment. Observations indicate that these geysers originate from a global ocean beneath the thick ice crust. These emissions contain complex organic compounds, hinting at the molecular building blocks of life. The relative accessibility of these plumes makes them a focal point for astrobiological exploration. Missions equipped with advanced analytical instruments could sample these materials directly, offering insights into the chemical processes occurring within the ocean. This region, with its potential hydrothermal vents, may also serve as a habitat for extremophiles, organisms thriving in harsh environments. Understanding the characteristics of Enceladus's ocean is crucial for determining its habitability. The presence of essential elements such as carbon, hydrogen, nitrogen, oxygen, phosphorus, and sulfur creates a biochemical foundation. This environment fosters speculation about the possibilities of life existing in an alien ocean, deep beneath its icy surface. Unique features distinguish this moon from its counterparts within the vast expanse of the solar system. Enceladus exhibits a smooth ice shell, with cracks and fissures known as tiger stripes, which are indicative of geologic activity. These features contrast sharply with the heavily cratered surfaces of moons such as Mimas and Tethys, which suggest a much older and more stable history. The youthful appearance of Enceladus hints at its dynamic processes, driven by tidal heating due to gravitational interactions with Saturn. Hydrothermal activity is another aspect that sets it apart. Plumes of water vapor and organic compounds erupt from its southern pole, revealing an active subsurface ocean. This phenomenon is not observed on other icy bodies, such as Dione or Rhea, where geological activity has largely ceased. The composition of these plumes is also noteworthy, containing essential ingredients that could support microbial life. The reflective surface, dominated by bright ice, is a stark contrast to the darker, more rugged terrains of moons like Hyperion, which bears the scars of impact cratering and erosion. These variations in surface characteristics and geological features offer crucial insights into the evolutionary histories of these celestial bodies. Enceladus, with its potential for habitability, remains a focal point for comparative planetary science and astrobiology. Understanding its environment enhances the broader narrative of icy moons in the solar system. This moon plays a pivotal role in astrobiological models and theories, primarily due to its subsurface ocean. Beneath a thick crust of ice lies a liquid water reservoir, rich in minerals and potentially suitable for life. The presence of hydrothermal activity on the ocean floor, evidenced by geysers that erupt into space, suggests that the conditions for microbial life may exist. These plumes, composed of microscopic particles, organic compounds, and water vapor, have been observed by spacecraft such as Cassini, revealing a complex interaction between the icy shell and the ocean below. The implications of these findings extend beyond mere speculation. They suggest that life could emerge in environments vastly different from Earth, leading to a re-evaluation of where life might be found. Such conditions challenge previously held beliefs about the necessity of sunlight for sustaining life forms. The chemical processes occurring in Enceladus Ocean, similar to those found in Earth's deep-sea hydrothermal vents, reinforce the idea that life can thrive in extreme environments. Astrobiologists continue to study this unique moon, using it as a model to consider other icy worlds in the outer solar system. If life exists here, it opens the possibility of life elsewhere, potentially reshaping our understanding of biology and its resilience. The search for answers continues, deepening the intrigue surrounding this frozen satellite. Innovative exploration technologies are being developed to unlock the secrets of Enceladus. One prominent approach involves the use of advanced robotic landers designed to penetrate the icy crust and analyze subsurface oceanic compositions. These landers will utilize high-resolution imaging systems capable of capturing detailed geophysical features to assess the moon's surface and its dynamic processes. Another promising technology is the deployment of autonomous aerial drones, which could navigate through the vapor plumes emanating from its south polar region. Equipped with sophisticated sensors, these drones will sample the plume's chemical makeup, providing critical insights into the potential habitability of the subsurface ocean. Orbital satellites are also set to play a vital role. Enhanced radar systems and spectrometers will map the moon's surface, revealing variations in ice thickness and revealing hidden geological structures. By monitoring thermal emissions, these satellites will track geothermal activity, shedding light on the moon's internal heat sources. Collaborative efforts among space agencies aim to develop missions that incorporate these cutting-edge technologies. They seek to establish a comprehensive understanding of this enigmatic moon and its role within the Saturnian system. Each mission is poised to contribute invaluable data, fostering a deeper appreciation for the complex interactions between celestial bodies in the vast expanse of our solar system. This understanding hinges on the unique characteristics exhibited by Enceladus. The moon's surface, cloaked in a thick layer of ice, reveals a dynamic geological history influenced by tidal heating. This process results from gravitational interactions with Saturn, leading to the presence of subsurface oceans. These oceans are crucial for comprehending the formation and evolution of icy bodies within this region. Surface features, such as the prominent geysers that eject plumes of water vapor and ice particles, provide insights into the moon's internal structure and composition. These plumes not only feed Saturn's rings but also serve as key samples for astrobiological studies. The ejected materials contain organic molecules, hinting at the potential for life in extreme environments. The icy crust acts as a protective barrier, preserving the underlying oceanic environment. Studying the interactions between the crust and the ocean can illuminate the processes that govern the development of icy worlds. This interplay shapes not only Enceladus but also influences the characteristics of other moons and bodies within Saturn's gravitational influence. Understanding these mechanisms enhances knowledge of how similar icy bodies throughout the solar system may have formed. Enceladus stands as a compelling case study, bridging concepts of planetary formation with the quest for extraterrestrial life in frigid environments. The icy surface conceals a subsurface ocean, a critical element in understanding habitability beyond Earth.
This hidden water reservoir is not merely a geological curiosity. It informs theories regarding the potential for life on similar celestial bodies. The geysers that erupt from the Moon's south pole release plumes of water vapor and organic materials, inviting analysis of their chemical constituents and their implications for astrobiology. Investigations into these plumes contribute to the broader field of exoplanetary research, drawing parallels between Enceladus and distant worlds orbiting alien stars. Some exoplanets, particularly those in the habitable zone of their respective stars, may possess conditions akin to those found on this moon. The study of Enceladus enhances the understanding of how life might emerge in environments previously thought inhospitable, further expanding the criteria used to define habitability. The insights gleaned from this moon influence the design of future missions to ocean worlds. Instruments developed for exploration may one day probe the depths of these distant, water-rich environments, seeking signs of life or biosignatures. Each discovery enriches the narrative of planetary science, illustrating how moons like Enceladus serve as vital links in the quest to comprehend the universe's myriad possibilities for life. This ongoing research continues to shape the trajectory of astrobiological inquiry. The intrigue surrounding this moon is deeply rooted in its unique geological characteristics and potential habitability. Key publications have emerged from extensive studies detailing the discovery of water vapor plumes erupting from its southern polar region. These findings suggest a subsurface ocean which may harbor the necessary conditions for life. The analysis of data from missions such as Cassini has provided vital insights into the moon's icy crust and the composition of its ejected materials. Research conducted by planetary scientists has shed light on the chemical makeup of Enceladus's ocean, revealing a rich assortment of organic compounds. These elements present compelling evidence that the environment might support microbial life. This region exhibits a dynamic interplay between the Moon and Saturn's rings, generating a continuous flow of material that feeds the vibrant ring system. This interaction highlights the profound influence Enceladus has on its celestial neighbor. Significant studies have focused on the Moon's internal heat generated by tidal forces, which maintains a liquid ocean beneath the surface. The implications of such heat sources are profound, as they hint at a potentially habitable zone existing within an otherwise frigid environment. Ongoing research strives to unravel the mysteries of this enigmatic moon, seeking to understand its role in the broader context of planetary science and the search for extraterrestrial life. The geophysical properties of this moon reveal a complex structure characterized by a relatively low density of approximately 1.6 grams per cubic centimeter. This value suggests a composition rich in water ice, interspersed with silicate rock and possibly organic compounds. Ice plays a critical role in shaping both the surface and subsurface geology, indicating a dynamic evolution influenced by internal processes. The surface features, including the vast plains and ridges, exhibit a variety of textures that hint at past and ongoing geological activity. These formations are punctuated by deep fissures known as tiger stripes, emanating from the moon's south pole. These cracks are crucial, as they are believed to be conduits for the subsurface ocean to escape, releasing plumes of water vapor and icy particles into space. The presence of these plumes suggests a warm, liquid water environment beneath the icy crust, a potential habitat for microbial life. Composition analysis indicates that the ocean beneath the surface may be in contact with the rocky mantle, facilitating chemical reactions that could support life. This interaction raises intriguing questions about the Moon's ability to harbor ecosystems. Understanding these geophysical properties is essential, providing insight into the processes that govern not only Enceladus, but also similar icy bodies throughout the solar systems. Currents within the subsurface ocean of Enceladus play a pivotal role in shaping its unique environment. The interaction between gravitational forces and the Moon's eccentric orbit induces tidal heating, maintaining liquid water beneath a thick icy crust. This heating creates temperature gradients that drive complex fluid dynamics. Warmer regions near the Moon's core contrast starkly with the frigid surface, establishing a system of currents that facilitate nutrient transport. These currents are not merely a byproduct of tidal forces. They contribute to the overall energy balance of this ocean. Variations in temperature influence the movement of water, generating a dynamic environment that could potentially harbor life. The icy shell above acts as an insulating layer, preserving the warmth below, while simultaneously creating a pressure-induced stability in the ocean. Thermal anomalies detected by spacecraft suggest localized hotspots where currents may rise to the surface, fostering a rich chemical environment. The interplay of these ocean dynamics leads to the periodic plumes observed ejecting from the South Pole, releasing water vapor and organic compounds into space. Analyzing the composition of these plumes offers a glimpse into the underlying ocean's characteristics, allowing researchers to piece together a comprehensive understanding of Enceladus's geophysical processes and their implications for astrobiology. The potential for energy sources in the subsurface ocean is a subject of significant interest. This hidden reservoir, shielded beneath layers of ice, presents conditions that may harbor a variety of energy-producing processes. Hydrothermal activity on the ocean floor could serve as a vital energy source, facilitated by interactions between the Moon's rocky core and its vast ocean. These interactions may lead to the release of chemicals, providing the necessary ingredients for life to flourish in environments previously deemed inhospitable. Thermal vents, similar to those found on Earth, could emerge from this geothermal activity. Such vents may support unique ecosystems, sustaining microbial life that relies on chemosynthesis rather than photosynthesis. The nutrient-rich waters, in conjunction with various minerals, create a dynamic environment where life may thrive. Understanding these ecosystems could unveil the intricate relationships between energy sources and biological processes. The presence of organic compounds in the plumes further suggests that basic building blocks for life are available. This intriguing combination of energy and nutrients raises the possibility of biologically relevant reactions occurring within these depths. Investigating the potential for energy sources in Enceladus's subsurface ocean not only informs our comprehension of extraterrestrial environments, but also enhances our understanding of life's resilience in the cosmos. The implications for future exploration and the search for life beyond Earth remain profound. The influence of Saturn's seasons extends to its moons, shaping the geological character of Enceladus. This region experiences drastic changes as the gas giants tilt and orbit, create variations in sunlight. The axial tilt of Saturn leads to seasonal shifts that last for approximately 7 Earth years, affecting the thermal dynamics of this icy moon. Temperature fluctuations induce stress within the subsurface ocean, which may promote geological activity. When sunlight strikes the surface, it warms the ice, causing potential melting at the crust. This melting can result in geysers, observed erupting from the South Polar region. These geysers, rich in water vapor and organic compounds, offer insight into the moon's interior and its ongoing geological processes. During the extended periods of darkness, the temperatures drop, allowing the icy crust to solidify and compress. This cyclical pattern of heating and cooling influences the formation of the surface features, including the ridges and fractures that characterize the terrain. Moreover, the gradual changes contribute to the continuous replenishment of the particles that feed Saturn's rings, a delicate balance sustained by the moon's activity. The interplay of these seasonal changes not only shapes the geology of Enceladus, but also plays a critical role in the broader dynamics of the Saturnian system, revealing interconnected processes spanning vast distances. The surface of Enceladus showcases a variety of terrain types, each offering insight into its geophysical history. Smooth plains, characterized by their low relief, suggest regions shaped by cryovolcanism, where subsurface water has erupted and frozen upon contact with the frigid environment. The presence of these plains indicates a dynamic subsurface, continually reshaping the exterior through geological activity. In stark contrast, the moon's more rugged regions display heavily cratered surfaces, revealing the age of these areas and their relative stability over time. The craters serve as a timeline, marking periods of impact events that have punctuated its evolution. The distribution and size of these features provide clues about the moon's collisional history and the frequency of extraterrestrial impacts in this region. Ridges and faults crisscross the surface, hinting at tectonic processes that have occurred in the past. These linear features likely formed from stress within the ice shell, suggesting that the interior of the moon may still be active. The diversity in surface morphology reflects not only Enceladus's geological past, but also its present state, characterized by ongoing processes that maintain its unique characteristics. Each element of the terrain contributes to a complex understanding of this icy world within the Saturnian system. The intricate surface features of this moon provide invaluable insights into the processes that govern planetary ring dynamics. Enceladus exudes plumes of water vapor and ice particles, a phenomenon that plays a crucial role in the maintenance of Saturn's rings. These eruptions, originating from subsurface oceans, introduce fresh material into the ring system, highlighting a continuous recycling of resources. This region, characterized by its geologically active nature, signifies a dynamic interplay between celestial bodies. The icy grains expelled by Enceladus contribute to the delicate structure of the E-ring, enhancing its brightness and density. The gravitational interactions between these particles and Saturn's immense gravity create a complex web of forces that shape the ring's morphology. Observations reveal that the interactions between the ejected materials and the surrounding environment influence the stability and longevity of the ring system. Such processes suggest that Enceladus acts as a pivotal player, not merely as a bystander, but as a contributor to the ongoing evolution of Saturn's rings. Understanding these contributions enables scientists to grasp the broader implications of ring dynamics across the solar system. Insights gleaned from the interactions of Enceladus with its planetary environment extend to other ringed planets, illuminating the fundamental principles that govern celestial mechanics. Investigations of Enceladus reveal a world where the conditions for prebiotic chemistry may exist. Underneath its icy crust lies a global ocean, sustained by tidal heating, which creates a dynamic environment conducive to the emergence of complex organic molecules. Plumes of water vapor and ice particles spew forth from fissures in the surface, suggesting not only the presence of liquid water, but also a potential reservoir of essential chemical ingredients for life. The organic compounds identified in these ejected plumes include simple hydrocarbons, which are foundational elements in the chemistry of life. This region serves as a natural laboratory, presenting scientists with opportunities to analyze its content without the necessity of landing a spacecraft. The composition of the plumes offers vital clues about the subsurface ocean's interactions with the Moon's rocky core. In addition to water and organic molecules, the presence of key chemicals such as methane and carbon dioxide hints at the possibility of metabolic processes, perhaps driven by hydrothermal activity on the ocean floor. Such environments on Earth host diverse ecosystems, thriving without sunlight. The conditions on Enceladus, while distinct, echo these terrestrial examples, prompting questions about the potential for life beyond Earth. Each discovery fosters a deeper understanding of how life may emerge in extraterrestrial locales. Positioning Enceladus as a focal point in astrobiology, the analysis of Enceladus has revolutionized perspectives within astrophysics and planetary science. Initially perceived as an icy body devoid of significance, its exploration revealed an active subsurface ocean, fundamentally altering the understanding of celestial bodies within the outer solar system. This moon's geysers, which emit plumes of water vapor and organic compounds, demonstrate geological processes that challenge previous notions of what defines habitability. The findings suggest that Enceladus, along with its unique composition, plays a crucial role in the dynamics of Saturn's rings. The particles expelled from its surface contribute to the maintenance and replenishment of these structures, illustrating a complex interplay between celestial mechanics and astrobiology. The energetic interaction between the Moon and the rings exemplifies the intricate relationships that exist in the cosmos, influencing both the physical properties of the rings and the potential for life in extreme environments. In addition, the detection of simple organic molecules within the ejected material fosters inquiries into the origins of life. This moon serves as a natural laboratory, offering insights into the early conditions that may mirror those of primordial Earth. The ongoing study of Enceladus continues to inspire interdisciplinary research, bridging the realms of planetary geology, astrobiology, and the search for extraterrestrial intelligence, highlighting its enduring significance in the broader landscape of scientific inquiry. Active regions on Enceladus reveal a landscape marked by geysers that intermittently eject plumes of water vapor and ice particles into space. These geysers emerge from a subsurface ocean, a significant reservoir beneath a thick, icy crust. The Cassini spacecraft recorded these eruptions, providing crucial insights into the Moon's geological processes. The surface, characterized by a patchwork of ridges, grooves, and chaotic terrains, showcases the Moon's complex history of tectonic activity and thermal evolution. Inactive regions display a contrasting serenity, where the icy surface appears older and more heavily cratered. The fewer geological features suggest a lack of recent activity, allowing impacts from meteoroids to persist over long periods. The stark division between active and inactive areas highlights the Moon's geophysical dynamics. Ice plumes originating from warmer subsurface layers create a significant interaction between the surface and the ocean below, suggesting a potential for life. These geological features contribute to the understanding of tidal heating processes, which may drive the moon's internal activity. The interplay between the moon's icy crust and the underlying ocean is a focal point in assessing its potential habitability. This duality of active and inactive regions paints a complex picture of a moon consistently reshaped by the forces within and beyond its icy facade. Remote sensing plays a crucial role in unraveling the mysteries of this moon's environment. Instruments aboard spacecraft, such as the Cassini orbiter, have provided invaluable data through various imaging techniques and spectral analyses. These observations enable scientists to assess surface composition and identify the presence of water, organic materials, and other essential compounds. The icy surface reflects sunlight, revealing variations in brightness that correspond to geological features. These variations inform researchers about past and present geological activity. Observing the plume eruptions from the southern polar region highlights active processes, suggesting a subsurface ocean that may harbor conditions suitable for life. The captured images illustrate not only the plumes themselves, but also the intricate interactions between the expelled material and the moon's surface. Thermal imaging adds another dimension to understanding this environment. Variations in thermal emissions indicate areas of geothermal activity, suggesting heat sources beneath the icy shell. This heat may contribute to the continual reshaping of the surface, providing insights into the moon's geological evolution. Spectroscopic data enhances the understanding of the chemical composition of the plumes, revealing the presence of organic molecules and salts. These findings heighten interest in the potential for astrobiological research within this intriguing celestial body, expanding our knowledge of the conditions that may support life beyond Earth. The allure of Enceladus extends beyond the realm of scientific inquiry, permeating popular culture and igniting the imagination of storytellers. This moon's icy surface and plumes of water vapor have inspired numerous representations in science fiction, where it often serves as a setting for exploration and discovery. Its unique characteristics, including subsurface oceans and potential hydrothermal activity, provide fertile ground for narratives centered on extraterrestrial life. In various works, Enceladus is depicted as a mysterious frontier, brimming with possibilities. It may appear as a refuge for humanity, a world where the remnants of past civilizations lie frozen beneath an icy crust. These interpretations often explore themes of survival and the ethical implications of colonizations. The presence of organic compounds on its surface encourages speculation about microbial life forms, often leading to confrontations between explorers and the unknown. Visual portrayals frequently highlight the stark beauty of its surface, contrasting the deep shadows of its crevices with the brilliant, shimmering expanse of its ice. Filmmakers and authors utilize this setting to evoke a sense of wonder, provoking reflection on humanity's place in the cosmos. Such representations not only entertain but also stimulate public interest in planetary science, fostering a deeper understanding of the universe and our quest to uncover its secrets. Interdisciplinary studies play a crucial role in unraveling the mysteries of Enceladus. This moon, with its icy surface and subsurface ocean, invites collaboration across various scientific fields. Planetary scientists analyze surface geology, while astrobiologists explore the potential for life in its hidden waters. These diverse perspectives combine to create a more comprehensive understanding of this celestial body. Geophysical data reveal tectonic features and cryovolcanism, suggesting a dynamic interior. The study of these phenomena benefits from the insights of geophysicists and chemists who examine the composition of plumes erupting from the Moon's south pole. Instruments aboard spacecraft, such as the Cassini orbiter, have provided invaluable information, measuring the chemical makeup of these plumes and offering clues about the ocean beneath. Astrophysics intersects with these studies as researchers investigate the Moon's interaction with Saturn's magnetic field and its influence on the surrounding environment. Understanding these interactions is essential for deciphering the processes that feed the rings of Saturn, enriching their composition with particles from Enceladus. The future of Enceladus research holds the promise of significant discoveries that may reshape our understanding of this intriguing moon. Missions designed to explore its subsurface ocean could provide valuable insights into the potential for life beyond Earth. The presence of organic compounds and the observed hydrothermal activity hint at a rich and complex chemistry beneath the icy crust. Increased attention from space agencies aims to send advanced landers or orbiters to Enceladus, equipped with cutting-edge instruments capable of analyzing surface and plume materials in greater detail. This region's geysers, which erupt water vapor and icy particles into space, will be prime targets for sample collection and examination. Sophisticated imaging techniques may reveal the Moon's geological history, unlocking secrets held within its surface features. Patterns in the ice could indicate past climatic conditions and the dynamics of its internal ocean. Enhanced spectrometry might identify molecular signatures that suggest biological processes, illuminating the possibility of extremophiles thriving in its dark depths. Predictions suggest that future missions will not only confirm the Moon's potential habitability, but also establish a more nuanced understanding of its role in the Saturnian system. As new findings emerge, the scientific community will grapple with their implications, broadening the horizons of astrobiology and planetary science. The interplay of light and ice reveals the intricate chemical processes occurring on Enceladus. When sunlight strikes the surface, it interacts with the icy crust, producing a unique spectral signature. This region's surface reflects light in ways that hint at hidden reservoirs beneath the frozen exterior. The icy plumes, which intermittently erupt from the southern polar region, contribute to the complex dance of particles and gases, enriching the study of this moon. Analysis of these spectral patterns indicates the presence of organic compounds, silicate materials, and a variety of other substances, each providing clues to the moon's geological and potential biological history. The ejected material, primarily composed of water vapor, plays a crucial role in feeding the intricate rings of Saturn, allowing for a dynamic exchange between the two celestial bodies. Ionized particles from the moon's plumes interact with the magnetic field of Saturn, creating a radiative environment that further complicates the analysis. Instruments aboard orbiters and landers have meticulously catalogued these phenomena, revealing a landscape shaped by both external and internal forces. The icy surface of Enceladus serves as a record of its past, a window into a world that may harbor the conditions necessary for life. This ongoing research highlights the moon's significance in understanding the broader context of celestial mechanics and planetary evolution. The moon's subsurface ocean presents a unique environment, fostering discussions around its potential for habitability. Beneath a thick layer of ice, this ocean remains in contact with a rocky seafloor, creating conditions conducive to chemical interactions. Such interactions may produce the essential elements for life, including organic compounds, as evidenced by plumes of water vapor and ice particles detected erupting from its surface. The detection of these plumes reinforces the notion that the ocean is dynamic and potentially nourished by hydrothermal activity. Temperature gradients across this oceanic layer suggest that pockets of warmth may persist, driven by tidal heating. This phenomenon results from gravitational interactions with Saturn and its other moons, maintaining a liquid state beneath the ice. The depth of this ocean, of immersive far, I've argis showed by Okavide estimated to be around 10 kilometers, provides a stable environment, insulated from harsh surface conditions. Okamorders of various salts and other chemicals within the plumes indicates a complex chemical landscape, further enhancing the moon's intrigue. These findings fuel ongoing debates among scientists regarding the likelihood of microbial life existing in such an environment. Investigations into the biochemical processes occurring in these subsurface oceans remain crucial, as they may yield insights into not only Enceladus, but also the potential for life on other icy worlds throughout the solar system. Understanding the diversity of icy moons hinges significantly on the characteristics of this celestial body. Enceladus serves as a vital reference point, showcasing a variety of geological features and processes. This small moon, with its smooth, reflective surface and numerous fissures, indicates a dynamic environment. These features suggest a rich geological history shaped by internal heat and tectonic activity. The presence of plumes erupting from its south polar region provides invaluable data regarding subsurface oceans. These geysers expel water vapor, salts, and organic compounds, which allow for direct sampling of the moon's hidden ocean. Examining these materials enhances comprehension of the chemical makeup of Enceladus and the potential for similar processes on other moons, such as Europa and Ganymede. Although this region demonstrates how diverse environments can exist within the icy bodies of the solar system, each moon possesses distinct characteristics influenced by factors such as size, distance from the Sun, and internal composition. Enceladus exemplifies an active world, contrasting with more geologically dormant moons. The understanding gained from studying its processes contributes to broader theories regarding the evolution and habitability of these icy worlds. Knowledge derived from Enceladus informs future exploration, encouraging missions aimed at unraveling the mysteries of other moons orbiting distant planets. Sparring through discoveries have propelled Enceladus research into new realms of understanding. The identification of water vapor plumes escaping from its south polar region revealed a subsurface ocean, hinting at the potential for life in environments previously deemed inhospitable. These findings have shifted the focus of planetary science, emphasizing the importance of icy moons in astrobiological studies. Instruments aboard the Cassini spacecraft analyzed the composition of these plumes, uncovering organic molecules and salts, which raises questions about the chemical processes occurring beneath the moon's icy crust. The data collected highlights the dynamic nature of this region, suggesting an active geological history that continues to evolve. Such insights have prompted further interest in the moon's internal structure and its thermal dynamics. The implications extend beyond Enceladus itself. Understanding its oceanic environment may provide parallels to other celestial bodies, such as Europa and Titan, where similar subsurface oceans are suspected. This interconnected web of research fosters a collaborative atmosphere among scientists, uniting efforts to explore the habitability of icy worlds across the solar system. The ongoing analysis of Enceladus continues to inspire new missions. Each discovery reinforces the significance of this moon, of the significance of this moon, illuminating not only its unique characteristics, but also the profound mysteries that lie hidden within the vast expanse of the cosmos. Enceladus plays a crucial role in understanding solar system evolution models. Its geysers, which erupt with plumes of water vapor and icy particles, hint at an active subsurface ocean. This phenomenon suggests that similar processes may have influenced other celestial bodies throughout the solar system. The presence of liquid water, a fundamental criterion for life, raises questions about the conditions necessary for habitability in environments beyond Earth. The Moon's surface, marked by chaotic terrains and ridges, indicates geological activity that may have persisted for billions of years. Such ongoing processes provide insight into the thermal dynamics and internal structure of icy moons. The relationship between Enceladus and Saturn's rings is also notable. The Moon contributes material to the E-ring, creating a dynamic exchange of substances that may influence ring composition and stability. Models of solar system evolution often consider the interactions between celestial bodies, including gravitational influences and material transfer. Enceladus exemplifies how one moon can affect its parent planet and surrounding environment, suggesting that these interactions may have been pivotal in shaping the solar system's architecture. The Moon's unique features invite further exploration and study, potentially revealing more about the history and future of planetary systems, as well as the conditions that foster life in the universe.
Rolf of R. Rohes of Asrenia's findings on Enceladus has significantly influenced the design and objectives of future missions. The discovery of plumes ejecting water vapor and organic molecules from the Moon's subsurface ocean created a compelling case for astrobiological research. This revelation prompted scientists to consider the potential for life beyond Earth, particularly in environments previously deemed inhospitable. Subsequent missions are now being planned with specific instrumentation designed to analyze the chemical composition of these plumes in greater detail. Such investigations aim to ascertain whether the conditions within the ocean beneath the icy crust can sustain microbial life. The knowledge gained from Cassini's observations has enabled mission designers to prioritize critical scientific questions, guiding the selection of landing sites and target regions for future exploration. The data collected by Cassini have also reshaped our understanding of icy moons across the solar system. The similarities observed between Enceladus and other celestial bodies, such as Europa and Ganymede, Ophirothemid Sunramumik, suggest that these moons may harbor similar subsurface oceans. This has led to a broader interest in investigating multiple objects within the outer solar system, expanding the search for extraterrestrial life. These advancements underscore the importance of continued exploration and the profound impact of Cassini's mission, fostering a deeper understanding of the complexities inherent in planetary systems. Enceladus stands as a compelling gateway to understanding ocean worlds and the potential for life beyond Earth. Its icy surface conceals a vast subsurface ocean, rich in the necessary ingredients for life. This environment is characterized by hydrothermal activity on the ocean floor, which releases minerals and energy, creating conditions similar to those found in Earth's deep-sea ecosystems. The plumes of water vapor, rich in organic compounds, emanate from fractures in the Moon's surface, offering tantalizing clues about its oceanic depths. The data collected by Cassini revealed an intriguing chemical signature, bolstering the hypothesis that these environments could support microbial life. The presence of carbonates and other organic materials indicates a complex geochemical landscape. These findings highlight the importance of studying such celestial bodies, as they may hold answers to fundamental questions regarding the emergence of life in the universe.
Amphorio, Olafetian. Exploration of Enceladus fuels aspirations for future missions aimed at directly sampling its ocean. Ophirothemid advised directly sampling its ocean. The quest for understanding extends beyond this moon. It prompts consideration of other icy worlds, such as Europa and Ganymede, each with their unique geophysical characteristics. Interdisciplinary research continues to illuminate the connections between these distant realms and life's resilience on Earth, reinforcing the idea that the search for extraterrestrial existence is not merely a scientific endeavor, but a journey into humanity's collective curiosity.